what I would like to do is first of all to show you why we call it backstepper controller. And then after that we can do one or two examples on how to apply backstepper. Right? And then we end the lecture with implementation using adapter. And exactly what we did before will repeat itself. It's exactly the same procedure. The system, dimensionality of the system can make the procedure very complicated in terms of math. Doable, but math, it needs to be a little bit more required, but otherwise it's exactly the same thing. So first of all, we are going to start with the structure of the system. This is a nonlinear system. The characteristic of the system is that the first equation is function of eta, and zeta appeared here alone. Zeta is the next state that you have in the system. At the end, we have zeta prime equal to u. So this type of system is called integral backstepping, okay, integral form, right? Because zeta prime is equal to u. There is no dynamic in the last equation other than the integration of u. So if we look to the realization of this, and I put it in block diagram, so I will have eta prime, which is here. It's equal to f of eta plus epsilon multiplied by g of theta, so the sum of all of them here. This will give me eta prime. If I integrate eta prime, I will get eta, and since I need eta and the f, I have this kind of structure. At the end here, this is the value of zeta. The value of zeta is the integral of u, or zeta prime is equal to u, so this is why we have u as that right here. So this is the integral backstepping that we are going to see here. Right, so the structure is simple in terms of form. So what are we going to do next? We are going to look to the system as we have, and then do exactly the same philosophy that we did with the feedback realization. We are going to say, let me assume a Lyapunvo function, v of eta is equal to eta squared, like this. V of eta is equal to eta squared. The system is going to be stable, or going to go to 0, if v prime is negative. So if I compute v prime of eta, it's equal, we are going to put half here just to remove the 2. It's going to be equal to eta prime multiplied by eta. And eta prime is given by our equation as f of eta plus g of eta multiplied by epsilon. Right? So my question is, can I find zeta here? Can I find the function zeta equal 5 eta that makes this derivative that we have here negative? Right? So basically the next state I have in the system, I'm going to use it temporarily as an input, and I'm going to ask myself, is there a way to stabilize this equation, the first equation, eta prime plus g of eta times 5 eta, using Lyapunvo theorem? Everybody is okay with this? The question is clear? All right. So let's suppose that there exists. We can find 5 eta. Right? We can call it 5 0 if you want. 5 0 of eta is the function that, or the value of epsilon equal to 5, to keep the same notation. Zeta equal to 5n is, if I replace it here and then replace it in this derivative, it will be less or equal to minus wn. Wn is, w eta is a positive defined function, so minus makes it negative. So this, the whole derivative is bounded by a negative term, so it's negative or equal to 0. And we are going to assume that this exists. Everybody is okay with this? Then I come back to my system, back again to my equation. So this one we found. We found how? Using Lyapunvo. So we come back to our equation eta prime. equal to f of eta plus g of eta multiplied by zeta. We add 5 eta and we remove 5 eta. In fact, zeta is equal to 5 eta, so this is g of eta times 5 eta minus g of eta multiplied by 5. So I did not do anything, right? Because it's a multiplication, it's addition to 0. Then I bring this system, this one and this one together, because I know if I put zeta equal to 5n, this derivative will be negative, so I'll put them both together. So this will be equal to f of eta plus g of eta phi of eta, and then plus g of eta multiplied by zeta that I have in this equation, not the value of theta, it's zeta here, minus phi of theta. So if we assume that zeta is really equal to 5 theta, so this term is 0, this system will be stable, because the Lyapunov will give you negative derivative. Everybody's okay with this? I'm going to call this one whatever, and I think in the slides I put them Z, if I'm not wrong. Right? So I'm going to call it Z. So this term is a new variable. Everybody's okay? So if we'd like to see what will be the equivalent of this equation that we have wrote here now, we took zeta, we removed from it 5 eta, so this is zeta, we removed 5 eta. We multiplied by g of eta here, right? And then we took eta, we put it in this equation, not only f of n, but f of n plus g of eta multiplied by 5 eta. So we took eta here, we plug it in this equation, we got here. So this system gives me basically this form. Any question up to now? Anybody has no idea what I'm talking about? يلا, you have a question? اللي وراك أحمد.
No, I have no idea.
So what's our objective now? It's a nonlinear system. And this nonlinear system, I would like to take advantage of its structure in order to find the controller, right? And the way we did it, we went step by step. We looked at the first equation that we have. This is our first equation. We notice zeta appearing here alone. There's no other zeta other than this. So if we have, for example, a system of 5 variables, only the next variable will appear here, not all the rest of the 4. So we have only this variable appearing. So I'm going to take advantage of the presence of this, and I'm going to ask myself, what will be the value of this zeta, such that this equation will be stable, go to 0, for example, right? And we assume that based on our calculation, based on our Lyapunov, we were able to find a function 5n that represents zeta in this dynamic equation, and this will be bounded by a negative function. This is positively defined. So from here, I re-manipulated the system such that now I have zeta minus the function that makes my system stable. So if zeta is equal to 5n, exactly equal, the system will be equal only to this, and based on my Lyapunov, the system is stable, right? Now I go back to the last equation that I have here. We have z prime is equal to zeta prime minus phi of eta prime, okay? And zeta prime is equal to u minus phi prime of eta, like this. Right?
We don't have phi prime.
We have.
We have phi.
We are saying that we will do an example, but we said that we were able to find phi of eta such that this A is negative using Lyapunvo. Yeah.
Previously we did a structure like that, we have cancelling the nonlinear terms of the system.
Right.
And we put a nonlinear controller in it. And it is acting like previously. So what is the motive of this backstep?
Backstepping is we don't do direct linearization with the system because it's complicated for us. The control appears in another equation, not in the full nonlinearity system. So they are not at the level of the controller, but the system has a particular structure, right, that we are trying to take advantage of. So if we continue like this, so we are going to take z equal to zeta minus phi of n. Eta prime will be given by this equation g of eta z, and then z prime is equal to u minus phi prime. So basically it's like you took, this is the variable z now, z is the integral of these two terms, and the function is function of z. So it's like you took phi of eta and you put it before the integrator, right? So this is the structure that we had before. This is phi of n, this is the integrator. And the next structure, based on my change of variable, phi of n moved from in front of the integrator, from to before the integrator. So this is why each time I'm trying to backstep the value of phi of n, which is the nonlinearity or the value that we have here, one step ahead in the equation. This is why we call it backstepping. So we step one by one, like this, right? In each state. All right, now the question is still what will be the value of u, right? So to find the value of u, we create again so we're going to write this here. We have eta prime equal to f of eta plus g of eta multiplied by z. Z prime is equal to u minus phi prime of eta. Phi prime of eta, by the way, is the same thing as the derivative of phi of eta. If it's only one variable, it will be the total derivative. So if you want, you can assume it's the one variable and we put total derivative with respect to eta multiplied by eta prime. Right? So this eta prime is given by this equation. So our objective is to find the controller. In the first, to find phi of eta, I use it v1 of eta equal to half eta squared. This is the one that gave me the value of phi of eta here. In the second attempt to find u, I'm going to use v2 of eta equal to v1 of eta plus half of z squared. Right? So you have Lyapunvo at the first equation. You do Lyapunvo in the first equation to find what should be the solution that will make the first equation stable. Then when you go to the second equation, you define a new Lyapunvo that will be equal to the previous Lyapunvo function plus half of the new variable that we are putting here. Right? So which is exactly half of eta squared plus half of z squared. This is the equivalence. So if we apply the same rule, we say the system is stable if v prime is negative. Then I'm going to take v prime. V prime will be equal to eta prime times eta plus z prime multiplied by z. Eta prime is given by 5 eta plus g of eta multiplied by z, the whole thing multiplied by eta, plus u minus, I'm going to put phi prime here just to make sure that we don't write too much. The whole thing multiplied by z again. Are you okay with this? Right. The derivative also of 5 eta, let me put it here. This equation is the same thing also as f of eta plus gn of epsilon, zeta, right? But it's just a manipulation of equation that we have here. So I'm able to replace this equation the way I want.
There is eta dot missing in the last u minus 5 dot eta dot times z.
When you say dot like this, it means the derivative that we have here. Right? Which is this one. Alright, so this is what we are going to get then. If we develop this equation, we are going to have f of eta plus gn of eta multiplied by zeta, right? There's something wrong here.
yes.
There's something wrong here.
Yes.
Yeah. So there is a 5n missing, 5
Yeah.
eta missing, plus g of eta multiplied by z, right?
Yeah.
So here we are going to have this g of eta, 5 eta,
First
Plus
with
z.
minus.
plus g of eta times z. Like that. So the whole thing, this one here, the whole thing multiplied by eta. I removed the value of eta here. So we are going to have eta multiplied by times eta. This is the first step. This multiplied by the value of eta plus eta, g of eta multiplied by z plus u minus phi prime, the whole thing multiplied by z. You agree with this?
Yes.
So this term I know the value of this term, right?
Yeah, it's them.
It's the value of the first v1 that I took, and it's less or equal to minus w1. W. So we are going to say v prime is equal to minus w eta, right? Less or equal normally, but we are going to say equal. You can put it less or equal if you are bothered with this. Plus eta, g of eta plus u minus phi prime, the whole thing multiplied by z. And the question now is, what should be u, my controller?
Solution.
Yes,
There's supposed to be an A to
they're supposed to be.
here. The eta
Yes,
outside.
this eta outside here. It's here.
Yes, but when we're integrating in the W,
What?
the expression for the W.
Wn is here, huh? Derivative of eta with respect to eta is eta
Yeah.
multiplied by eta prime. What should be u?
1 over Z. Minus eta G.
How should you select u?
What do you want to cancel?
What do you want to
All
cancel?
of this is equals 0.
All of this equals 0. So let's say that we decide that all of this is equal 0. Because we have the control, huh?
Yes.
This is our controller. We can decide that everything here is equal to 0. Then we will have 0 times z, and then v prime will be negative. Everybody agrees with that?
Yeah.
The problem if I do this is that the negativity of the derivative does not depend on z, the second variable. It's completely independent. So z could be anywhere and I'm not aware of it. Okay. So how can we correct this? Force also z to be 0.
Minus lambda z.
Huh?
We add minus lambda z.
Minus lambda z. So rather than making it equal to 0, we make everything equal to minus lambda z. Like this, we will have minus lambda z squared that we'll add here, and then if this becomes negative, means both eta and z are going in the negative direction. Everybody is okay with this? So we will have u equal to phi prime minus eta g of eta minus lambda z. This is your control. How did we find it? We did not go directly to the control. We started with the state, and then we went to the next state after that, in order to make sure that the control is defined. Right, so we will take an example. So, all this is explanation, but we will take this example here. Right, x squared minus x1 cubic plus x2. So this is x1 prime is equal to x1 squared minus x1 cubic plus x2, and x2 prime is equal to u. So you can see here in the first equation that x2 appears linear, so the system, right? This is not like g of eta that you have there, right? And it appears alone, so I can take x2 and see what I can do with this, right? So I declare v1 equal to half of x1 squared, so this is my Lyapunvo, and then I will take derivative v prime is equal to x1 prime multiplied by x1, and x1 prime I will put x1 squared minus x1 cubed plus, let's say, u1 or phi 1 or whatever you call it. Huh? This is the value of x2 that will make this derivative negative. The whole thing multiplied by x1. So how can we make it negative?
Sure, you want is
U1 plus.
cancels.
Why you replace x2 at u1?
Because I'm looking to the particular value of x2 that will make this dynamic stable.
Sure.
So it's one particular value, right? One particular function. And I will push my system to go to this function in the next step when I look to the Lyapunvo for both. So I'm looking to this phi of eta. This phi of eta is u1 in this case. Okay, I called it for you u1, so you know that it's like an input. It's a virtual input to the system. So what should be the virtual input for us here?
x1 cube minus x1
So we will have u1
x1.
x1 squared minus x1 cubic plus u1. This has to be
Minus lambda x1.
minus lambda x1. Same thing that we did before. Or minus x1. Everybody agrees with this? Alright. So if I do this like this, it will work. It has no issue at all. I can implement it. But because the system has a nonlinearity which is equal to x cubic, so there's a difference between x squared and x cubic, right?
Yes.
X squared, you cannot differentiate between x positive or x negative. Both of them will give you a positive value. So the controller does not know how to act. Right? If he's above, it gives him positive. He's below, it gives him positive. He has no idea. He has to push up or push down. So we cannot do anything. Cannot design the controller. But for x cubic, if it's positive, it's positive. If it's negative, it's negative. So if I'm above, it gives me positive value. Below, it gives me negative value. I can differentiate.
Can we eliminate x1?
Huh?
Can we eliminate x1 with u1?
Can I do what?
Eliminate x1 and just stay with x1.
X1 squared, you mean?
Yes.
So we can just eliminate x1 squared and remain only with
Yes.
x1 cubed. U equal to minus x1 cubed. But if I put only u equal to minus x1 cubed,
Don't have
when
control over the
x1,
speed.
sorry,
Don't have control over the speed.
we don't have control over the speed. Especially when x1 is very small.
Very small.
When very small, I lose the value of x1 cubed. So the best thing to do, rather than having only minus lambda x1, we are going to say that this value I will not cancel. I will keep it here. So I will put minus x1 cubed. So I will remove this. Sorry, this one and this one are the same. I will put u1 equal to minus lambda x1 minus x1 squared. Everybody understood the understanding? There is no problem of putting minus lambda x1 only for all of it, so we can cancel all the terms that are nonlinear. But cancelling all the terms that are all nonlinear, you are going to lose the impact of this x1 cubed, which can help you to be even better stable when x1 is large. And when x1 is small, the lambda x1 will take over. So the convergence to zero close is divided above 1 and below 1 by this nonlinearity that we have here. Everybody understood what I'm saying? Yes? Huh?
So the judgment call?
Okay.
The judgment call or there's a rule for
A
it?
judgment call. Yani look to this one here. It's like the control works for you like a range control. A range controller is a controller that gives you, depending on where you are, far or away from the system. If you are away from the system, it gives you large control action. If you are close to the system, it gives you smaller control action. Right? A range controller is implemented in the industry using two valves, one big valve and one small valve. So when you are close, we are using the small valve because we want fine precision. But when you are very far, we want to be there as fast as possible.
But if x1 is negative, then the derivative will not be equal to negative. If x1 is negative, then x1 cube is negative minus it will be positive.
I don't
But it's
care.
multiplied by x1 outside.
Yeah, but I don't care also because all what I need is the derivative of this Lyapunvo, not the second derivative. For now, there are cases where we go to the second derivative to see if we are stuck in a certain place or not, or is it the inflection point or others. But let's assume that you are in a region where there is nothing such behavior.
This is actually what happened for assuming your speed. If you are controlling the speed and then you make a break, then you press the resume. If you are far away from your desired speed, he will give you acceleration, low to acceleration. That's why.
Yeah, that's true. Can you imagine, for example, you have a robotic arm and you would like to go from here up to here.
Yes.
Are you going to apply the same control values and speed as when the robotic arm is here? Okay. If you do it, because when you are very close, you need to make small steps in order to make sure that you converge to the point, especially if you are doing precise maneuvers, right? But if you are very far and you do exactly the same thing, you will stay eternity before arriving here. So we take advantage of the size of the controller that we have to make it very quick convergence. When we are close to the target, the equilibrium point, which is 0, this term will lose energy, right? It's very, very small. So this one will take over. Everybody understand what I'm saying? All right, so basically what at the end we are saying is that it's sufficient for me to select u1 equal to minus x1 squared minus lambda x1. So basically I cancel this term, and I add minus lambda x1 in the equation. And this, as you see, is function of x1. So this is why we had phi of eta. So here is phi of x1. Everybody is okay? So this equation that I put here is assuming that I'm using x1, the value of x2 as an input. So I will come back to my equation here and I will say x1 prime would be equal to x1 squared minus x1 cubed plus x2. And I will add plus minus x1 squared minus lambda x1. And I subtract minus x1 squared minus lambda x1. This is the meaning of adding and subtracting phi of 8. Everybody is okay with this? So these two terms, I will take them together. This term, I will bring it here. So I will have x1 squared disappears. Minus x1 cubic will stay. Minus lambda x1 will stay. So I will have minus x1 cubic minus lambda x1 plus x2 minus this term, right? Which is phi of x1 or u1, the way you want, whatever makes you comfortable. So I'm going to put here phi of x1 just to make sure that you link with the slides. Everybody is okay with that? You can see here if x2 is equal to phi, this term stays. Why? Because if I take this term and I plug it here, this will be negative. Make sense? All right, so the next step, I'm going to rewrite here everything, back again to this, plus phi of x1 minus phi of x1, and this will give me minus lambda x1 minus x1 cubed plus x2 minus phi of x1, and I'm going to call this z. All right with this? So based on this equation that we have z prime is equal to x2 prime minus phi of x1 prime, total derivative with respect to time. This will be equal to u minus phi prime. So derivative here of phi prime is this value, huh? That we have here. So derivative of this with respect to time, I will have derivative with respect to x1. So minus 2x1 minus lambda. The whole thing multiplied by x1 prime. And x1 prime is given by this equation or this equation, the way you want. So everything is well defined for us. So this is the first stage. The second stage now is, what is the value of u? So I declare a new Lyapunov function, v2, and this time v2 will be function of x1 and x2, or z1 and x1 and z, the way you want. Right? So we can put here z just to be consistent. And this will be equal to half multiplied by x1 squared, which is the value of v1 x1 that I used before, plus half of z squared. Agree with this?
The second Lyapunov function, we use it to try to make the stability for the input, to be sure about the stability of the input. Or
Basically what I'm trying, if you look at it carefully, I'm trying, you see here I assume that I have the control input x2, and I find that if x2 is equal to this value, then the system will be stable. In the Lyapunov, I'm penalizing the difference between x2 and this function. So I'm trying to force x2 to go to 5x1. And then by putting all this together, I will select this value of u that will make it happen. So if I select the value of u, that will make this system stable, x1 will go to 0, and x2 will go to 5x1. واضح؟
That's why I have a question.
Yeah.
If if we want x1 to not to go to 0, to go to a certain point,
Right. So now you have to rewrite the whole equation in the design value of x1.
x1 minus
x1 minus x1 design prime, and then you continue. Okay? You rewrite it, the whole thing as a function of dynamical derivative. This is why here we are talking about x1 going to 0, because we are assuming that the equilibrium that we are targeting is 0, which means that it's the error between what you want and the actual system. We are okay with this? Alright. If I used phi of x1 equal, u of x1 equal only to minus lambda x1, I ignore the x1 cubic, it will work. But it will give you a slower system. Right? But it's the same thing. طيب, we take the derivative. So x1 prime multiplied by x1 plus z prime multiplied by z. This is v2 prime. This will be equal to minus lambda x1 minus x1 cubic multiplied by x1 plus x2 minus phi of x1 multiplied by x1. So this is basically x prime times x1. Right? Or this is basically z for us, z multiplied by x1. And then plus z prime. Z prime, we have it equal to this value, right? But to make it short, I'm going to take only this, right? So we are going to write x2, u minus phi prime of x1. Multiplied by z. By z. Z is this, huh? So this is also z. So this term, I know it is negative. x1 minus lambda x1 squared minus x1 to the power 4. I know it's going very well to 0, negative. So what I need to do is to define u such that this term that I have here is also negative as a function of z. Everybody's okay with this? So basically we take z as a factor. Z as a factor will give me u minus phi prime as a function of x1 minus phi of x1 multiplied by, not phi of x1, minus x1. Right, so this is this term and this term, the whole thing multiplied by z. I take this and I make it equal to minus lambda multiplied by z. So I will have u equal to phi prime of x1 plus x1 minus lambda z. This is your input and your controller for the system.
Plus x1 plus x1.
So u, this term equal to minus lambda z. So we take everything to the right side. So this will be plus, and this one is plus. Everybody understood the process?
No, I meant sir before.
Before
Should be plus then negative. I think.
Should be plus initially here.
And initially, yes, here.
This one?
Yeah, it's plus z, plus z.
This one is plus.
Plus z and, yeah.
Plus Z.
You're right.
That's actually.
It's, so this one is minus. You agree with this? يلا شباب.
Yes,
عامل وقت عشان لازم فينا شات يس ولا نو. We make it a little bit more complex,
No, not now.
just to understand the process, how it works. So now everything is fine, sir, for this system. Yeah. So we are going to change the system again. And redo it as if we did not know about the system as it is. So basically we are going to come here and we say x1 prime is equal to x1 squared minus x1 cubed plus x2. x2 prime is equal to x3 and x3 prime is equal to u. So how many times you are going to apply the procedure? 3 times. Right, so you focus on the first equation here. As we did before, so v1 equal to half of x1 squared. This will give you the value of phi 1 of x equal to minus x1 squared minus lambda x1. This is what we found. This, huh? So if I replace this phi 1 here in this first equation, I'm going to get x1 prime equal to minus lambda x1 minus x1 cubed, which is stable. So I go back to this first equation, it becomes x1 prime equal to, I will add and subtract, right? So I will have minus lambda x1 minus x1 cubed, like what we did in the previous one. Yeah, plus x2 minus phi 1 of x2. And this I'm going to call it Z. Z1.
Have another set.
Because there is another Z coming, huh? Type Z1 prime, it will be equal to x3 minus phi 1 prime as a function of x1. So the question now is, what's the value of x3? So we do exactly the same thing. We define the Lyapunvo function v, and here now we are going to have v1 plus half of z1 squared, which is equal to half of x1 squared plus half of z1 squared. The derivative v prime equal to x1 prime times x1 plus z1 prime times z1. Everybody's okay with this? So let's do it. I don't know, this class has a very limited space. So I'm going to remove this right on the top. So here we find that the value, this is like u in the previous example. And we find the value of u. So this is phi 2 of x1, x2. It's equal to u2, which is the place of x3. So we cannot be confused, huh? And we found what? We find that this is equal to minus x1. صحيح? Last equation that I wrote for you was what?
minus
x1 minus lambda x plus phi dot
Minus lambda.
minus x1 minus lambda lambda
Minus
z1
x1
minus lambda z1
minus lambda z1
Plus
plus phi dot over
plus phi dot. Phi dot of x1, right? And you know phi dot of x1 is derivative, total derivative with respect to time. So it's the derivative with respect to x1 times x1 prime. Huh? Partial derivative. So this is your phi 2 now. So your system changes. Now we will have x1 prime equal to minus x1 minus lambda x1 minus x1 cubed plus z1. z1 prime, I'm going to add phi 2 and subtract phi 2. So if I add phi 2, I will have, it was what? This one was equal to x3. So I will add plus phi 2 minus phi 2. Everybody is okay with this? This is the phi 2 that we just found as a function of x1 and x2. So this will be equal to whatever value that we have. We are going to put x minus phi 2 together. So this will be equal to phi 2 plus x3 minus phi 2 together, like this. We know what's the value of phi 2, huh? This is the one in the top that we have here.
minus x1
Done with this, we are going to call this value
Sorry, Prof.
z2. Yeah.
But z1 dot is x3 minus phi dot of x1.
Z1 dot.
Yeah, that's it. Down.
Yeah, we have minus phi prime. Thank you very much. Phi 1 prime. Right, so minus phi 1 prime. In fact, because we are going to cancel this term that we have in the equation. Thank you. So this is your value of z2. We take z2 prime is equal to u minus phi 2 prime. Right? This is the value x3 prime minus phi 2 prime. And this is u minus phi 2. What should we do next? Lyapunov. Again, we go back to Lyapunov. So Lyapunov will be equal to v will be equal to half of x1 squared plus half of 0 squared plus half of z2 squared. And then you take the derivative to make this thing. To find the value of u, that will give you this negative. So what I'm doing basically in this, I'm pushing x1 to 0, I'm pushing the value of x2 to phi of x, and I'm pushing the value of z2 to phi 2 of x1 and x2. Everybody is okay with this? Clear? So if my target is to reach 0, 0, 0, state x1 0, state x2 0, state x3 0, these functions phi 2 of x1 and phi 1 of x1 have to verify phi 1 of 0 is 0 and phi 2 of 0, 0 is also 0. Otherwise, you are going to converge only on one variable, which is x1. Everybody is okay with this? What I did make sense?
So you need to verify.
Huh?
We need to verify.
We need to verify. So if you go back to the slides, you will see that we are going to assume that these phi's they have phi of 0, for example, here is 0. So we can converge to 0, 0, the equilibrium point. Make sense? Right? So let me give you an example. Now this is, you are going to do this.
So are we making this assumption, or this is known already from our equations?
Which one?
That phi of 0 is 0.
If we, because we are looking, for this system, 5, 0, 0 is verified.
Yeah, it's 0, yeah.
But for the previous example, where we are trying to find g of eta such that and minus w of eta, you need to verify that 5, 0, 0.
Okay.
Because this one has no way to find it unless you replace by something.
But we have lambda
Which one?
minus lambda x1 for example.
Yeah, it's okay.
How we can go to 0?
Minus lambda x1 when x1 is 0, lambda
Yeah.
x1 is 0.
Yeah.
All right. I'm going to change the example, very simple example. X1 prime equal to theta times f of x1 plus x2, and x2 prime is equal to u. And we are going to assume that theta is known. So I would like you to tell me what should be the value of the controller. Take a piece of paper and try to repeat this again. Can I take a picture of the first? Please, can you take it? Uh, So who would like to guide me here?
Lyapunvo.
مارك ترك في شيء ما واضح في شيء واضح ولا في شيء ما واضح تمام نتكلم بعدين طيب ان شاء الله Try to see which part you are blocked. You don't know how to continue, so you can ask questions later. Right, let's do it together. Are you ready? Let's do it together. So what should I do first? Yeah, no. We can assume x2 equal to u1 if we are rather playing with x2. But we can leave it as it is. So we are going to put v1 equal to half x1 squared. Exactly the same thing that we did before. Then we would like to derive this v prime, which is equal to x1 plus x1, and make sure that it is negative. This will be equal to theta times f of x1 plus the value of u1 if you want. The whole thing multiplied by x1. So what should be the value of u1?
Minus
So u1 is equal to minus lambda x1 minus theta f of x1. So this is like feedback realization. You cancel the nonlinearity and you add a term to make the system stable. So this is your phi of x1. We are all okay with this? Alright, then we go back to our equation. We are going to have x1 prime equal to theta f of x1 plus x2, and then we add and subtract the same function that we found here. So I will put plus phi of x1 minus phi of x1. When I put plus phi of x1, this term will cancel this term, Only minus lambda x1 will stay, so this is minus lambda x1. And then I will have x2 minus phi of x1 plus x2 minus phi of x1. And this I'm going to call it z. So next time, what should I do? Take z prime. Huh? Z prime, it will be equal to x2 prime. x2 prime is u minus phi of x1. And phi of x1 is minus lambda x1 minus theta f of x1. So this will be equal to u minus lambda x1 minus, sorry? Dot, yes. Thank you. F of x1. The whole thing derivative. So it will be equal to the same thing. This will be equal to u minus, I'm going to write it because maybe we need it later, but otherwise we will repeat it again. So this will be x prime, and here there will be an x prime out. The derivative of x1 with respect to x1, theta is now a constant. So I'm going to put here minus lambda minus theta, derivative of f with respect to x1. And in the previous lecture, we put dash like this to show that this is derivative with respect to x1. The whole thing multiplied by x1 prime. And x1 prime, I have it, it's here. You agree with this? So derivative of this with respect to time is this term with respect to time. So it's x1 prime. Minus theta f of x1. So derivative of f with respect to x1. Maybe I'll put it like this, is better. Derivative of f with respect to x1 multiplied by x1 prime. So I took x1 as a factor. Oh. What should I do next? Lyapunov again, so V. In this Lyapunov, my objective is to find U. So V is equal to half of x1 squared plus half of z1 squared or z squared. We take the derivative, v prime, and we select the value of u that makes this v prime negative. So the rest is manipulation, math, to find what should be the value of u.
Yes.
Everybody agrees with this?
Okay, so if we have a lot of steps, like 20 steps or something, we derive any time at the beginning, or there is another?
There's no order. You derive step by step.
So in real life, we will have a lot of steps. Should we avoid it?
You decide. You remember what I told you before about control? A box. You open, you have a screwdriver, you have I don't know, the screwdriver machine or manual or whatever, you select the tool you want.
So please, if the states, if we have the system who doesn't have this structure of the
We cannot
state.
apply backstepping.
Okay.
Backstepping has particular rule to apply. It's this structure. Otherwise, you can.
Like, can we make our dynamics to have something closer?
Sometimes you can, sometimes you can. So if there are transformations that will bring my system in the structure, I will do it. Otherwise, so you can do it. طيب شباب وشابات. Ladies and gentlemen بالانجليزي. I'm going to assume now theta is unknown. So up to here everything is exactly the the same. What I'm going to find is that u1 has to be equal to minus lambda x1 minus theta multiplied by f of x1. This is the value of u1 that we found in the previous problem when we solved it before, sir. But the value of theta is unknown, so this controller is not feasible. So in order to make this controller feasible, I need to put an estimate of theta. Right? An estimate of theta. Now I go back to my equation. I have x1 prime equal to theta f of x1 plus x2. And then I need to add and subtract this phi of x. Everybody's okay with this?
Yes.
So I will put plus minus lambda x1 minus theta hat f of x1 plus lambda x1 plus theta hat f of x1. This x2 and this term, they will go together. So this is x minus phi of theta. And this term, they will not cancel each other.
You don't compare.
Because theta is unknown, and this is the estimate. There is an error between the two. Everybody's okay with this? So I'm going to put here, this will be equal to minus lambda x1 plus theta minus theta hat f of x1 plus x2 plus I'm going to put here u1 just to make sure that, or let me write it here, plus lambda x1 plus theta hat f of x1. You agree with this?
Yes.
So this is your new z. It's the same thing as before, as we did in the previous example, except now rather than having theta, we have theta.
We know this. Exactly. Yes.
We are going to call this as we did before,
Yeah.
theta tilde. So if I take the derivative now of z, the derivative of z prime, it will be equal to x2 prime. In this case, it's equal to u plus the derivative of this term, so plus lambda times x1 prime, derivative of this, plus the derivative of this term. So this will be equal to plus theta hat dot derivative of theta multiplied by f of x1 plus theta hat f dot or derivative of f with respect to x1 multiplied by x1 of it. This is your new derivative. Everybody agrees with this? Anybody has a question up to here? What I'm doing? No questions? Now x1 dot is this term, right? Or this term that we have here, which is minus lambda x1 plus theta tilde f of x1 plus z. You agree with this? So what will be my Lyapunvo?
So, theta as well.
So my Lyapunvo V2 now, the last step, huh? Remember the second step here. V2 will be half of x1 squared
Plus half theta 2.
plus half of z squared plus
Half theta 2.
half theta tilde squared.
Do you need control?
And we need the control that makes this negative.
And we don't have
Derivative of
to.
this negative. So basically in this Lyapunvo, I added the variable that I need to take to 0, my control, plus the error in terms of estimation parameter. I want it also to go to 0, right? To reduce it to 0.
We can.
So what will be the output of this if I took V prime negative? system is stable, but how I'm going to guarantee that this one is
Adaptive.
adaptive? So I'm going to find not only u,
It's also
but also how theta will change, u prime, theta prime. Everybody's okay with this? So if I take the derivative of this will give me x1 prime times x1 plus z times z prime plus theta tilde prime times theta tilde.
We can the gamma term here, leave it.
Sorry?
We can leave out the gamma term to control
We can
the
put gamma. If you want, you can put gamma here. It's always good to have gamma because you want to wait between the parameter estimation and the state stability. So this will be equal to x1 multiplied by minus lambda x1 plus theta tilde f of x1. So plus z. So that this is x1 prime plus z prime. We computed z prime. So this is z prime, which is sorry, I'm going to put z multiplied by z prime, which is u plus lambda x1 prime plus theta hat prime f of x1 plus theta hat multiplied by f dash, just to make sure that we don't write too much, as a function of x1 multiplied by x1 prime. And x1 prime is the same prime as we have here. So we have minus lambda x1 plus theta hat f of x1 plus z, appearing in this equation. Plus theta tilde multiplied by theta tilde prime.
Again.
With gamma. So the idea is to go and fetch all what is related to theta hat, theta tilde, right? Anything related to theta tilde, we are going to put it together with the system. So we have theta tilde that we multiply the step coming from the multiplication here, and we have theta tilde at this level, and the rest are function of u. Everybody is okay with what I'm saying here? So this basically, I'm saying here that this will be equal to x1 multiplied by minus lambda x1 plus z plus theta tilde x1 f of x1 plus z times u plus, I'm going to take x1 prime all as a factor here. So I'm going to put here theta prime f of x1 and then we're going to have here plus lambda plus theta tilde f prime multiplied by minus lambda x1 or x1 prime, right, which has theta tilde also again here.
Theta tilde or theta hat?
This is theta hat here inside. And this one is x prime as a factor of all of this.
Z. There's still Z.
There's still z multiplied by z.
Then with the last term for the
Correct.
theta dot.
Plus theta tilde prime multiplied by theta. Sorry? We can separate it later, it's fine. So for this one here, I see that it can make it very complicated if I replace here also by theta tilde that we have. But we remember this is only manipulation of equation. So it's exactly equal to the previous equation, which is theta times f of x plus x2. So I can come and just plug it here. Right, I will sense it and I plug it here inside here. So we have here theta tilde divided by gamma again. So I'm going to find theta tilde prime is basically equal to, or should be equal, I'm going to cancel these two terms. So theta tilde prime is equal to minus gamma x1 f of x1. If I do this term and this term, we cancel each other.
And another, it's also stable.
Sorry?
In the previous one. Same as the previous one.
Exactly. This one is stable already. We know it's stable. So I take z as factor of
Yeah.
everything. So plus z multiplied by
X1.
x1 plus theta hat f of x1 plus lambda plus theta hat f prime, the whole thing multiplied by x1 prime. And there is u missing, plus u. The whole thing multiplied by z. So I will force this term to be equal to minus lambda z. Right. So this will give me the value of u.
Depends on the theta hat.
It depends on
Theta hat.
theta hat, right? Here theta prime. Depends on theta hat. We don't care about theta hat. This is a prime coming from here, huh?
Yeah.
But we have this equation with us. So from here I can get the value of u. That we cancel everything, make it lambda z1. Is function of theta hat, the estimate, which is okay for me. But it's also a function of theta hat dot. So I will have to go to this equation. And I will know that theta tilde prime is basically theta prime minus theta hat prime. We said that theta changes path very slow, so this one is almost zero. This is equal to minus gamma x1 f of x1. So this will imply that theta hat prime is equal to this. Huh? And I take this value of function and I plug it here. Everybody's okay? Any question about what I did? So mathematically it becomes
Complicated.
this is second order system. You want to do it for third order system? It's done in the slides. In the slides is there for third system, but there is a small mistake. I will bring you to I will show you the error later on. But any question about what I did? No question? Last? This one here? So we have here theta tilde prime is equal to minus gamma x1 f of x1. I just separated, maybe, I'm sorry, sometimes this is the equation. But we said that this is very small, it's going to zero because it changes but very slowly compared to the system. So this is exactly minus phi theta hat prime, which is equal, according to my equation, to minus gamma x1 f of x1. So from here I can extract what should be the value of theta hat prime, which is this one here. I replace it in the controller first. The controller is physical. The control requires from me that I know the states and the derivative of x1 prime, but this is just measuring the states, getting them out. We did not talk about observer or how to get the state estimation. This is something else. Any question about what I did? No questions? Clear? Congratulations, this is your first backstepping, adaptive backstepping.
A lot of math.
A lot of math.
Need practice.
We need to practice, exactly, we need to practice. Don't wait until the exam to start practicing because it will be too late. So these are the maths that you have in your slides. Huh? By the way, these slides I took from my slides in nonlinear control, but you don't need to know all of this, so I'm going to take only one part and put it for you, only the examples that are relevant here, but you need to practice. You need to practice. Any question related to what I did today? Is everything what I did clear? Right. The system that we use today are called strict feedback systems. Strict feedback systems are systems that are described by, even if you have many states. So we say that the system is in a strict feedback form. So this is the structure of the system. You have the first state is only function of the second state, Z1. Okay. The second state can be function of the first, but it's function only of the next one, not the one after. So each time you are able to use one of the states as an input for you as a control, until you reach the last equation. Each time you define the Lyapunov function, and then you try to find what should be the input for you there. In this example, I used integral backstepping, which means that the last state is dot equal to u. But it could be any other function, general, like this one that we have here. I also used only one parameter, theta of f of x, theta times f of x1. I told you theta is unknown. But I could have theta 1 times f of x1 in the first equation, and theta 2 times f of x2 in the second equation, and another parameter in the third. And each time you go, you need to increase the Lyapunov function.
Maybe you can change the form. Same as the feedback normalization.
That's right. We can use the. This is like iterative feedback realization, basically. This is what
You see that in the exam.
Sure.
You see that in the exam.
والله عرفتوا فكرة خاطئة ترى والله. You're making bad publicity for me here. طيب, what I will do next time with you is sliding mode control. Right? So again, we will start with the sliding mode controller, how we implement sliding mode controller, and then we convert it to other. And it's exactly the same thing that I did here. We find the controller as function of the unknown parameters, then we replace them by the estimate, we plug them back in the equation, we find that theta tilde will appear there, and then we declare Lyapunov or sliding mode controller based on this theta tilde. Sliding mode is a little bit different because we have the reachability condition that we have to satisfy, in addition to the uncertainty of the parameter that we have also to keep on track. Any question? What I did is clear?
Is there any MATLAB implementation?
MATLAB implementation? I have, but I will show you this next time, inshallah. So, Wednesday, sliding mode control. If we finish sliding mode control on Wednesday, then lecture for next week, we'll do it as practice. If you would like to have problems, we can do practice.